In this video, I will explain the problems that the Pilot 4 within the ELOQUENCE project is addressing, and I will also explain how we could exploit AI to address these problems, with particular attention to the fact that the problem concerns a case where timely and accurate answers are of critical importance, the case of medical helplines. The main point is then, what is the best way to exploit AI in such a scenario, having in mind its limitations. The name of the pilot is Upgrading Support Call Centers through AI-based supervision of multimodal dialogues, and it is owned by the Faculty of Technical Sciences, University of Novi Sad in Serbia. Within the project, the objective of the pilot is to simulate an environment of unstructured dialogues arising in contact centers offering safety-critical responses, as is the case with medical helplines. Specifically, the case we are addressing are medical helplines intended to provide callers with medical assistance related to their young children, including newborns. Today, there are many examples of such helplines, some of them in Serbia. Young parents calling these helplines to seek advice about their children are often unsure what to do, anxious, or even frightened. On the other side of the line are trained medical professionals doing their best to provide safe and timely guidance. But the traditional system, where nurses answer calls directly, has its limitations. First of all, in this conventional setup, each nurse handles one telephone line. Thus, when demand increases, callers must wait, sometimes for long periods, before anyone even begins collecting information. Finally, when a nurse answers, a large portion of every call is spent asking the same structured questions: the child's age, symptoms, duration, medications, etc. So, highly trained medical staff spend valuable time performing repetitive intake tasks instead of focusing on clinical reasoning. The result is longer calls, increased fatigue, and greater risk of misunderstanding. So, what if information collection could begin before a nurse becomes available? In a chatbot-supported system, callers immediately interact with an intelligent conversational assistant. The chatbot asks questions, guiding parents step by step, collecting symptoms, timelines, measurements, and relevant history. So, waiting time becomes productive time. We have an example of such a dialogue here. After initial greetings, the caller is informed that he or she is speaking to an AI system. The system then explains its purpose, which is to collect some information about the caller's inquiry while the caller is waiting for a nurse to become available. The speaker then proceeds to explain the problem. Let's say it's a problem concerning a redness of the skin of the baby. The system, according to its dialogue strategy, collects general information, but also asks for details related to the information that the user has provided. If asked to provide medical advice, the system politely declines and reminds the user that the nurse or another medical professional that will take over the call will also provide all the advice. So this interchange between the user and the system can last for a minute or, say, several minutes. In the actual use case, it will depend on the availability of a nurse that is supposed to take over the call. In a simulated environment, it could be defined arbitrarily. Anyway, at some point, the system will inform the caller that a medical expert is available and that the call will be transferred to them. At that moment, the information collected from the caller is summarized and presented to the medical expert in a visually convenient way. He or she may double-check the accuracy of the summary with the caller, maybe ask additional questions for clarifications, and focus on what matters most: interpretation and decision-making. So to summarize, the system is intended as support to medical staff offering advice to parents of young children. This includes prevention, general inquiries, as well as actual situations, including also emergency situations. What should the system be capable of? It should handle the communication with the caller, which requires dialogue management, as well as speech technology, text-to-speech synthesis, and automatic speech recognition. The system should be able to summarize the collected information and present it in a visually convenient way to the human operator, which requires automatic summarization. In a realistic scenario, there is also a possibility that even after all reasonable questions the system may ask are exhausted, there is still no medical expert available. That is, they are all still busy with other conversations. In that case, a useful feature of the system would be to offer to read some general advice from a reliable source, such as a database of appropriate texts verified by medical professionals. For that to be possible, some sort of information retrieval is also needed. This would be an example of the structure of such a medical database. All the information is stored as answers to fixed general questions, And based on the caller's query and the collected information, the system can find a text that may be of interest to the caller. So the system may say something like, "Thank you, I have nothing more to ask, and the nurse will be available soon. In the meantime, I could read to you what our authorized source says about, say, skin redness in the diaper area." Within the project, the use case is simulated through the interaction of simulated clients with a server based on a large language model, which acts as a simulated call center. The diagram on the right shows the interconnection between different entities and modules in the use case. We see the user here. He or she interacts with the system through an appropriate web interface and maintains a dialogue with the LLM-driven dialogue management module. This module works with text, but receives speech from the user and responds with speech too. So it has to request speech recognition and speech synthesis each time to convert between speech and text. At the end of the conversation, it has to generate a summary. It sends a request for text summarization and receives a summary from an appropriate module, and possibly also retrieves a content-dependent text corresponding to the user's query from an authorized source using information retrieval. All this can be shown on an appropriate timeline. So the system first greets the caller and states its purpose. To do that, it has to request speech synthesis. This first statement can, of course, be pre-recorded or cached. The audio is sent to the caller then responds with another statement, etc. The component denoted as IP in the top row is the interactive playground of the ELOQUENCE project, which is a platform that collects and makes available the ELOQUENCE LLMs and tools, allowing us to test the model's language generation capabilities with different prompts and context information. Through this platform, the communication is further maintained in a loop of requests for information that the system sends to the caller and the caller's responses, prompting new questions. Finally, a request for summary is sent to the summarization module through the LLM, and the obtained summary is displayed to the medical expert, who also interacts with the system through an appropriate web interface. Subsequently, a request for information retrieval is sent to an appropriate module, and the retrieved text is converted into speech and sent to the caller. The trickiest part here, of course, is for the system to know what to ask at any given moment. It has to learn to focus on relevant information that is still missing, prioritizing safety-critical information, and for all that, it has to exhibit adaptive language understanding. To learn that, it has to be provided with a text corpus from which it could learn all these things. One of the principal roles of UNS at the ELOQUENCE project is data provider. UNS has developed a bilingual Serbian and English corpus of 150 dialogues obtained through recording sessions, followed by semi-automatic transcription and subsequent revision of the transcripts. Each recording session involved two participants enacting a conversation such as those that may actually occur in a call center of this type. The part of the caller was performed by team members who are also young parents, predominantly, while the part of the AI agent was performed by actual medical nurses. The issues discussed in a particular conversation, as well as its general directions, were previously arranged between the participants, but the conversations did not follow a predefined script. The callers discussed imaginary issues with babies based on similar events from their own experience. The conversations were carried out over mobile phones, and the audio recording of each conversation was captured. And as the primary purpose of the recordings was to obtain textual transcriptions suitable for use as LLM fine-tuning material for a medical chatbot, in the transcription process, the number of filler words and hesitations was reduced, grammar and sentence structures was made more formal, overlapping speech was identified and converted into a more formal representation. All that was done by hand. This resulted in a set of documents loosely based on the transcriptions of existing dialogue recordings, which were then revised by medical experts to maximize their verisimilitude. In one version of the corpus, a section used for testing purposes, the part of the AI agent, utterances spoken by the nurse, have been substituted with synthesized speech. Additionally, the corpus, both the Serbian and the English version, were annotated for entity types, as shown in this slide. For instance, I brought my son from the kindergarten. There, kindergarten is environment, a place where the child is or was, where they could get hurt or catch flu or anything like that. Then he constantly complains. This describes behavior and is thus annotated. About leg pain, this is a symptom, etc. This was done to enable exploring different approaches in the development of a successful dialogue strategy. So we come back to our initial question: how to exploit AI in a safety-critical scenario? We should exploit the capabilities of AI, but also be aware of its limitations. Although at this point we cannot let AI provide actual medical advice or give recommendations, let alone perform call priority assessment for ethical reasons or for legal ones, AI is still extremely valuable as a support to medical staff. By separating information collection from medical reasoning, we create a system that is faster and less stressful for both parents and medical staff. Thank you for your attention.